Okay, good evening, everyone. Tonight's presentation will be Exoplanets in Resonant Chains by Daniel Fabrycky, professor from the University of Chicago. During planet formation, while embedded in a gas disk, planets are expected to be pushed into orbital period resonance with each other. About 10 systems of 3 or more planets in resonant chains have been found orbiting other stars. Over the history of those systems, tides on the close-in planets, raised by the host stars, tend to spread the systems out. From these dynamics, we may soon infer the internal material properties of Earth-like and super-Earth exoplanets with and without massive gaseous atmospheres. Dan grew up in Arlington Heights, Illinois, after visiting the coasts for his education, Caltech Physics BS 2003, Princeton Astrophysics PhD 2007, and postdoctoral fellowships. He returned in 2012 and is now a professor in the Department of Astronomy and Astrophysics at the University of Chicago. His work has been recognized by the Sloan Research Fellowship in Physics and the inaugural Vera Rubin Early Career Prize from the Division on Dynamical Astronomy of the American Astronomical Society. Please welcome Professor Daniel Fabrycky.
All right, thank you. It's a great pleasure to be here. I'll try without the mic, and yeah, if the voice fails, we'll go to the mic. But I am going to talk about a number of projects over the years, starting about 7 years ago, and it's with a team of collaborators listed here from all sorts of institutions, notably a lot of students from University of Chicago. And we'll get right into it by explaining where the data come from. So the data will mainly be from transit missions, which means the planet's going in front of the star. And to measure that, we just take images of the sky. So the first one that did this with extreme precision to be able to measure the Earth-like planets around Sun-like stars, it's called the Kepler mission, and it flew about a decade ago now. And it continued for another 4 years in a mission called K2. It was a search for Earth-like planets by this transit technique. So it had to monitor about 180,000 stars straight through, just for 4 years. And it was in orbit around the sun to make the instrument nice and stable thermally. Its successor is called the TESS mission. It's also a NASA telescope. It's actually 4 telescopes mounted on the same payload. And it tiles the sky to a greater extent, a wider field of view with smaller telescopes. And therefore it's focusing on brighter host stars for close-in planets. So it doesn't dwell for 4 years, but for 28 days at a time. And then it's been revisiting the fields over the last 4 or 5 years. Because it's going after very bright host stars, it's good for follow-up in radial velocity, that's RV, and transit spectroscopy to measure the atmospheres of these planets. So I'm not going to go into the follow-up so much in tonight's lecture, but just talk about some of the discoveries from both of these missions. This one is not in orbit around the sun, but it does want to get away from the Earth a bit for thermal stability. So it's in a large orbit around the Earth with half the moon's period. Okay, so what do the data look like? They look kind of like this. You have the brightness as a function of time. Here's over 1 year of data from one particular case of the 180,000 stars in Kepler. The data are treated a bit to make it as flat as possible up here. But you see the small scatter, it's just about a part in 1,000. And then these excursions down here are dips due to planets passing in front of the star. Almost periodically, not perfectly periodically in this case, because we have 3 planets, Kepler 30. So the star is called Kepler 30. And we have 3 planets, B, C, and D, around this star. 2 of them have periods close to an integer ratio, 2-to-1 ratio, 60 and 30 days. And so, as we'll find out, this is a good situation for the planets knocking each other around in order to measure their masses and then their resonant properties. All right, so this is 30, so you should start to suspect that Kepler found a lot of planets. In fact, a lot of planets in multiple planet systems. So you can see the dots down here just tell us when those individual transits came for each of those planets. And the curves down here are the same data, just phased up, putting all their transits together and then drawing a model through it. So it turns out that Kepler found about 4,000 planet candidates, including about 700 systems of multiple planets. And the best way to illustrate that is not by a table or something, but by a little video. So here's the Kepler orrery. This is now almost 10 years old, this plot. So this is as part of a research group that studied these planets in particular. Here's for scale, here's the solar system's inner 4 planets. And there's a 7-planet system, which was an 8th planet was added later. So this is the behemoth. There's a 6-planet system here, and just a bewildering set of sizes to these planetary systems. You notice that Mercury here at 88-day period around the sun, there's tons and tons of planets much closer into their stars. So we can watch them tick by their years on, we can see many hundreds of orbits in just a few years of our ticking around our star. So we're diving into the very short orbital period planets, and before you all get hypnotized, I will move on. So what kinds of planets were discovered with this mission? Well, here's a histogram of the sizes of those planets. The scale is Earth radius, so here's 1 Earth. So most of the planets it found were bigger than the Earth, but what's on the axis here is the number of planets per star with periods less than 100 days. So it's really focusing your attention on the close-in planets. And what was found was a bimodality in this histogram. There's one set of planets that have masses, well, their sizes are a little bit bigger than the Earth, and probably their masses between 1 and about 1.7 Earth radii. And then there's a dip in the distribution there. So it looks like there's 2 populations of planets. One that are probably rocky, like the Earth. We've measured their masses in some cases and found that their densities are very similar to the Earth. And then up here above 1.7, well, if you do the math with constant density, that's getting pretty dense. It's like 6 or 7 times the mass of the Earth. And then we find a population of sub-Neptunes at sizes bigger than that. When we were able to calculate their mass by various methods, I'll tell you about transit timing in a moment, we find that they're often around 5 Earth masses, so their density is much lower than the Earth. They have an envelope of gas on top of them. The typical amount of gas is about, and the gas I'm talking about is hydrogen and helium. Those are the most cosmically abundant gases. And just 1% in the mass of the planet in hydrogen and helium is enough to puff them up by about a factor of 2. So this is what the structure we think of these planets, and that's why we call them sub-Neptunes. Neptune has about 10% of its mass in hydrogen and helium. And then out here on the tail of the distribution, there's the occasional gas giant. Turns out that about half of stars have a planetary system in these architectures around 100 days or less for their orbital periods, and multiple planets in a lot of them. And on the other hand, gas giants are much more rare. They're only around 10-15% of stars. They typically live out at 1 AU or further, so hundreds or thousands of day orbital periods. There is the very first exoplanets that were found were hugging their star with just 3-day orbits, but that's not at all typical. That's coming in at like 0.5% of stars have a hot Jupiter. so-called. So these gas giants out here are pretty rare close into the star. All right, so one thing that we can do with this wealth of multiple planet systems is just take a ratio between the periods of the planets. And that's what's done in this plot. It's not quite a histogram for the aficionados. It's called a kernel density estimator, KDE, but it's like a histogram. So you have peaks telling you how many planets there are within a certain bandwidth at all of these locations. And it's broken down by by whether you're all pairs or just the adjacent pairs or just two planet systems. But the upshot is that the distribution is pretty broad. It has a broad peak around 2 to 3 in orbital period ratio. The other thing I want you to notice, especially for this talk, is that there are some features near the resonances. So I've helpfully labeled the resonances here. 2 to 1 is the one I just mentioned for Kepler 30. And it has a peak really close to it. Not exactly on it, but slightly off to the side. And then 3 to 2 is another one that's populated quite well with a big spike here that's much bigger than the baseline. And if you keep staring, you'll see that there is a bit of a feature near 4 to 3 and 5 to 4. So these are called first order resonances because the numbers are different by 1. And they're dynamically important because even if the planets have nearly circular orbits, they'll feel perturbations from each other via these first order resonances. All right, so the upshot is that most planetary systems just have planets scattered all about. They don't necessarily perturb each other very strongly or care about each other's orbital ratio, but there is a set of systems that do. In fact, they're correlated. There's some systems in which multiple planets pile up in resonance with each other, and therefore I introduced the resonant chains. I'll first show you the orbital periods of these, the pairs. Then I'll mention some other ones. But the 4 that I'm going to talk about in detail tonight are Kepler 223, Kepler 80, TRAPPIST-1, and Kepler 60. So a lot of Kepler emphasis. But the first one has very close to resonance pairs. So that it's within a part in 1,000. The orbital period ratios are right on the 4 to 3, then 3 to 2, then 4 to 3. Kepler 80 has 4, and then a 5th one was discovered in the resonance. And they have period ratios just wide of 3 to 2, just about 1% wide in all cases. 3 to 2, 3 to 2, and then 4 to 3. 1.333 would be 4 to 3. And then TRAPPIST-1, it has a couple of third order resonance and the second order resonance, but then 5 planets in first order resonances, 3 to 2, 3 to 2, 4 to 3, and 3 to 2. So you're seeing that 4 to 3 and 3 to 2 are very common. And Kepler 60, an even tighter pair at 5 to 4 and 4 to 3. But again, just barely wide of them. So we have to learn why planets like to be in these period ratios and also why they like to be just barely wide of them. So here's the images looking down on these systems. And I promised in the abstract there's about 10 of these systems, so I'll just list the other ones. K2 and TESS have found these 3, so also in transit. And they all have 4 or more planets in these resonances. And then previously the radial velocity technique, which was the one that found hot Jupiters first, just 5 years after that, they found the first 2 to 1 planetary system, and that turned into a 4 to 2 to 1 planetary system around GJ876. There's another one known by radial velocity now, and I would argue that the 4 planet system known by direct imaging is probably also in a chain. All right, so I told you about the ratios of periods. How about the planets themselves? on that earlier plot, I showed you that there's super Earths and sub-Neptunes. Now I'm just showing you where each of these systems, its planets fall. So we have a variety. TRAPPIST-1, it actually has Earth-sized planets and some sub-Earth-sized planets as well. And then Kepler-80, its inner planets are super Earths. Kepler-60, it's kind of straddling. It's right between this, so it probably has some thin atmosphere on top of those planets. And then Kepler-223 has very thick atmospheres. So we have an opportunity to check the differences in all of these kinds of systems. I'll just mention that the innermost planet of these systems are what really matter for the physics I'm about to describe. So I'll just show you those only here. And then I'll just flash up some results of dynamical analysis that show us what the orbital periods are, but also what the orbital eccentricities are, and the masses. How do we get that kind of table? Well, we analyze exactly when the transits occur. I hinted earlier that they're not perfectly periodic. And so this is a slide showing transit timing variations for the 4 planets of Kepler-223. The scale here, sorry, it's a bit of an eye chart, this one, but it says transit timing variations in minutes, and the scale is about 100 minutes for the inner ones and a couple hundred minutes for the outer ones. And what you notice is that, what does it mean, transit timing variations? It's whether the planet arrives early to the star or late to the star, given its past history. But really, we just analyze that at the end of 4 years, checking what the average orbital period is, and then asking each transit, do you arrive early or late? So late would be towards the top of the plot, and early would be towards the bottom. And so we were able to measure, for instance, the outer 2 planets are torquing one another. As one boosts its orbital period to longer orbital period, the other one takes that energy and goes to shorter orbital period. So they're very coupled, and so you see an anti-correlation between those results as they perturb one another. And the same thing for the inner 2. And in fact, it's all resonant, because a 4-to-3 resonance right next to a 3-to-2 resonance makes a 4-to-3-to-2 resonance. And then you have a 4-to-2 between the inner and outer, and that gives you a 2-to-1. So all the planets are really in the ring together, fighting each other, so to speak. And so this was an analysis that once we had corrected all those timings, then you can see those dips for those planets. It was a tough analysis because you couldn't easily see the individual transits, so we had to invent a technique called photodynamics to analyze the system, where we used a n-body code. N is 5 here. You have the star and the 4 planets, and just using Newton's gravity to perturb one another as they go along their orbits, you see when the planets are coming on in front of the star from our perspective, and then make a light curve based on that. Synthesize what the telescope would see from how much light is blocked by each of those planets. All right, so that gives us these gray curves on this plot. Yeah, all right. Also, since they're perturbing each other so much, you need to impose long-term stability. It doesn't come for free. Just because they are orbiting stably over 4 years, it doesn't mean they'll keep staying stable. And so that was also applied here. All right, so what we infer happened here to get into the resonant chain is that they started out at maybe a few AU and then moved in towards the star. The outer one apparently moved faster. It was able to catch up to the inner ones and fall into resonance with them. So I'll show that again. You have the orbital period ratios between each pair, diving down to the 3-to-2 and 4-to-3 locations. So there's when they do that, they'll start transferring torque between each other. So the idea is there's a gaseous disk which forms the planets. Some of that gas goes on top of the planet, making it a thick atmosphere. But as the planets are still embedded in the disk, they get pushed around by it. They transfer torque to it and decay towards the star as a result. And so what I'm saying here is that the inference is that they migrated in, perhaps from much further away. Right now we see them at the 7-day period through 19-day period, but they could have come from a few AU, in fact. And that would naturally form the resonance and keep them in resonance, and they can just keep on scooting towards the star while in resonance. All right, so that explains how they got their period ratios, but now we have to think about how those other systems got spread away from resonance. So here's Kepler 80, and I mentioned that its offsets are just about 1% from the individual resonances. So you can do a little numerology, which we did in right around Christmas of 2010, when we first saw this discovery of these planets and were able to calculate their orbital periods. The numerology is figuring out what the period of the transit timing variations would be if we were able to measure them. That's a formula that depends on the resonance, whether it's a 3 to 2, J to K would be 3 to 2. And you can work out the frequency at which they are offset from the resonance, and then form that frequency into a period. So this is, for those of you who are, I know a lot of you are amateur astronomers, and you calculate like the synodic period for how often we're going to pass Venus, or rather Venus passes the Earth in orbit. Well, you would just put a 1 here for J and K, and Earth's period and Venus's period, and then you can calculate the synodic period. What's the time between us coming while Venus appearing in the same part of the sky? So it's a similar calculation to that, and we find in this system that these offsets give us the synodic periods of 192 days. And to our great surprise, it was the same for each pair in this system. So the frequency offsets are equal, and in fact, before the last planet was discovered in the light curve for this system, it was possible to predict what the orbital period is for that planet. And so it was found and could be seen to be a valid planet immediately from its orbital period matching this pattern. Okay, so something about the spreading also has a time scale that we'll get to momentarily. But first, I just want to show the plot that of some evolutionary simulations I did, which are the orbital period ratios. First, they're coming into resonance like we saw before with Kepler 223. Here's 3 to 2, 3 to 2, and 4 to 3. So they trap into resonance and get right to within about part in 1,000 of the resonance. But then what I've done here is I've put orbital eccentricity damping on the planets, and then stopped the disk effect. So there's something that's causing their orbits to dissipate in eccentricity, go down, become more circular, but nothing that's continuing to push them in towards the star. And the effect of that is to cause their orbital periods to scoot out to the observed ratios. So they all match the observed ratios all at the same time, and so that gives you these frequencies. So here's the orbital eccentricities pushing down as a function of time, and in concert with that, the orbital period spread. All right, so the upshot here is that it's not just a two-body resonance, in fact. It's not just 3 to 2 or 4 to 3, but there's something else called a three-body resonance, which enforces the offsets being equal in each of these pairs. So the latest, greatest calculation of this was a student and me at U Chicago working on 3 planet systems, and we surveyed a bunch of possible resonances. Like this is a grid of from 2 to 1 and 2 to 1 down to 5 to 4 and 5 to 4. And we found what the equilibrium situation would be for each of these systems. It turns out that as the eccentricities are going away, it just turns the phases of each of the planets matter. So as they become more and more circular, they're still interacting with each other gravitationally, but it's not through their orbital eccentricity, it's just their phases. So what you see in the labels here are combinations of the phase. So this was originally done for Jupiter's moons, Io, Europa, Ganymede, by Laplace. He noticed that a combination, that would be this combination, 1 minus 3 plus 2, was librating around 180 degrees. This is called the Laplace resonance, 4 to 2 to 1 for those moons. And it's the exact same thing, but now applied to exoplanets. And what we found was that when we form all those coefficients the right way, it's also 180 degrees in these systems. There's some slight exceptions, but it's usually at 180 degrees. What's fantastic about this is that it's just the orbital phase. It doesn't have to do with exactly how circular orbit is. And what that means is that we can use the transit data to determine the orbital phase and see that they are indeed in this resonance. That was done for Kepler 80 here, and a prediction was made for what the orbital, those three-body resonance where they should live, and that's what the data say, in fact. So what I'm saying is that they conspire to determine their phases in such a way that the orbital frequencies have these mathematical properties. You have a question in front here.
Yeah, this is the second slide I've seen with something very odd on the horizontal axis.
Okay.
Where it looks like maybe you go to 25,000 years and then decide to speed up.
That's true, yeah.
Okay, can you
it's just
explain
compressed.
Split?
Yeah, so the split plots back here was the same thing.
Yeah.
I decided to do that just so that I could show a longer baseline without resorting to a log time plot, which is kind of hard to conceive of. So this is just, yeah, it's another factor of 10 shown here. Instead of out to 25, it's out to 250.
Okay.
Now, this 10 to the 3 years, that's way shorter than the lifetime of the system. So, in fact, these damping rates are artificially fast. So to get something, well, I'll reveal the physical mechanism in a moment. All right. So it has to do with tides in the planets. What causes the eccentricities to get more and more circular over time? Now, we're familiar with tides, of course, the moon raising tides on the Earth in the oceans, but planets as a whole can also, the solid body part of a planet can flex. And if you're close into the star, as opposed to just having a close by moon, say the orbital period is less than 30 days, well, you have a giant star sitting there raising a giant tide on these rocky bodies, or the gaseous envelopes that I've talked about. So we would like to know how to consider tides. There is a tidal constant in the treatment of tides. It's been somewhat measurable for many, many years in the solar system. The Earth tide is this Q parameter comes in around 40 just because the oceans are give us so much dissipation. But the solid parts of rocky planets put us at several hundred. And then tides operate on the gas giants too, due to the moons around the gas giants. But being gaseous, they don't. There's not much dissipation in those systems, so they don't cause orbital evolution so readily. And so the Qs are much bigger. The lower the Q, the more dissipation there is. So this is for any physicists or one-time physicists in the audience. This is the parameter that we use to. It's called the quality factor, and it has to do with oscillations. So if you have a bell oscillating, its oscillations will damp out by a factor of E after Q oscillations. All right, so we can start measuring the material properties of these planets based on what we can derive for their damping coefficients. So in this analysis, we can assume that all the planets of Kepler-80 have the same Q, and they've spread for the lifetime of the system, which is not very well constrained, but it's between about 1 and 3 billion years. And the results of that analysis, what I'm doing is scaling up that eccentricity damping timescale that I quoted on the last slide to interpret it as a tidal damping coefficient. And what we get is that they have to be more dissipative, less dissipative than Q of 20. Otherwise, they would have spread further from the resonance. Their eccentricities would have been shoved down further and their periods moved apart more. But there should be some dissipation. Otherwise, this three-body libration amplitude would have been larger. So what I'm talking about is back here, there's this angle and it's oscillating at just a few degrees. If you had stopped the dissipation early on in the history of the system, it would have been oscillating at tens of degrees. So that gives us indication that there was some damping. All right, and then the closest in planet in the chain has a 3-day period, and it's a super-Earth type planet. So we're getting indication that the super-Earth has some material properties like the rocky planets of the solar system. All right, now you'll think back to Kepler-223, and I said that those planets had not spread from the resonance. So we can play the same game for it and apply some dissipation and wait until the planets have spread far enough away from the resonances that it no longer agrees with the data. So that's like, this is pushed out to 1.51, and I said no, it's really close. It's about 1.5001. So this gives us an upper limit on dissipation for this system, which has about a 6 billion year lifetime. It comes in at over 2,000 as a Q. So that's larger than the rocky planets of the solar system and appropriate more towards the gas giants or the ice giants of the solar system. Okay, another analysis with the same type of idea sets the Q value for Kepler-60's planets at a lot higher even, at least 67,000. So now we're getting up towards those values of Uranus and Neptune. All right, and then finally, of the 4 systems, I want to tell you about TRAPPIST-1. So this was originally a ground-based discovery of just the inner planets of the system. And then a spacecraft called Spitzer from NASA was able to detect all 7 planets. Kepler, in the K2 phase, was able to confirm the final planet, the outer planet. And so you'll notice that their names, I should have mentioned this with Kepler-60, but their names start with B, assigning A to the star. And then, so this system's really neat. It goes B through H. And the periods start at 1.5 days out to 19 days. And then I haven't inverted to get the period yet in this column, but you see here, it's the same numerology we played before, but now with the frequency. So this is frequencies in cycles per day. And you'll notice that these 4 all agree at 0.002. So you invert that and you get 490 days for all the pairs in this system. The upper 2 are just 2 times that and 3 times that. And you'll remember I mentioned these are 2nd order and 3rd order resonance. So it really all comes true. It all works out that they too have 3-body resonances among each of the pairs, each of the triplets. So I've been talking about these angles, and I know it's a bit abstract, so I thought I'd make a video of what that means. So here's the 7 planets of TRAPPIST-1, and let's just throw away the inner 4 and focus on these guys. So what it means for this angle to be 180 degrees is that when 2 of the planets cross one another's from the perspective of the star, the 3rd planet is on the far side of the star. It's 180 degrees away. So that's a similar thing to what Laplace realized for the Galilean satellites. All right. Then I also mentioned that transit timing variations could help us constrain masses, and that was best done for TRAPPIST-1 among small planets, at least. So here's a press image of measuring the size of the planets based on how much light they block as they go in front of the star, and then measuring the mass on scales as the planets perturb one another. So yeah, this is another eye chart, sorry. The labels are very small, but what we have is transit timing variation in minutes, and now the scale is just 5 to tens of minutes. And what you see is these oscillations are the 490 days showing up in the data. So we were able to see the planets perturbing one another. This was led by a colleague, Eric Hagel, at University of Washington. And what's over here is just subtracting off those big 490-day oscillations. You do see some extra variations on top of that. That's simply the planets passing one another on an orbital timescale. They're torquing each other up and down. It's only the 490 days comes in because those orbital timescale torques get amplified on the synodic time, 490 days. They add up, and then they add up coherently on that longer timescale. So what was determined here were masses of the planets that are some number times 10 to the minus 5 the mass of the star. In this case, the mass of the star is only about 0.1 the mass of the sun, 10%. It's a tiny, tiny star. That also gives us a great way to measure the sizes of the planets, because the data just tell us what the planet's area ratio is compared to the star's area ratio. So we're able to see very small planets and make this fantastic plot, which is the planet radii versus planet mass in the system. And what you can see is that we have lines of constant composition. These are theoretical planets. If you combine a bunch of silicates and iron cores together, and then perhaps put a water or steam envelope around it. So no hydrogen and helium anymore. We're talking about water of varying masses. So that gives us all these lines. But the upshot is that the densities are agreeing quite well with the planets in the solar system, and their masses and radii are very close. So this is, what's more is that the equilibrium temperature for some of the planets is quite habitable. We have not detected yet water on these planets, but some of the middle planets, like planet E, if it had water, it would be in a liquid form. So that's pretty exciting. We might know about the atmospheres, even whether they host water, in the next few years with detections of this system with the James Webb Space Telescope. All right, so to come back to the main theme, we did migration and damping simulations of this system. I'm starting here not at 1 AU, but much closer in at periods of just a few tens of percent longer than their observed orbital periods, and shoving them into resonance puts them deep into those resonances, but then the eccentricity damping pushes them back out to their observed orbital periods. So that's this plot. And what's more, we can in the simulation derive the three-body angles, and those almost completely, it's not perfectly clean, but almost completely match with the data. All right, and then we can do the scaling of the damping to get Q prime, and that gives us a few hundred, as in the rocky planets of the solar system. So not only does the mass and radius look like it agrees with the solar system planets, but the Q values, which have to do with the flexing of the body, seems to be the same as well. What's a little strange about this one is because the inner planets are not in first order resonances, damping allows their eccentricities to go down to very, very low values. And so on the longer time scale, the damping that causes spreading in this system is dominated by planet D a little bit further out. So that's this planet. And it's a little washed out, but there's a gray region here, which is a very generous habitable zone defined by having liquid water, the ability to host liquid water. All right, so I'm going to come in on a landing here to summarize the gains we've had, which are that resonant chains leave fossil evidence of a history of migration and of tidal damping. And we are starting to sense the interiors of sub-Neptune class, super-Earth class, and even Earth-sized planets with the TRAPPIST-1 system. And what we can see is that they differ. So if we put on a crude mass radius diagram for these systems, and I emphasize the planets that were dominating the dissipation in each one, then we can put those limits or ranges of Q values. So here they are. We have, for the sub-Neptune planets at a little bit larger radius as a function of mass, we have several thousands for Q prime, and then for the super-Earth planet and the Earth-like planet, we have more like a few hundred. And so the contrast of these two planets right here that are without an atmosphere and with a thin atmosphere is that it looks like the gaseous layers can keep their interior from cooling, maybe keeping the rocky interior molten. That's probably certainly the case for Kepler 223, but for Kepler 60, B, C, and D, it may be the case as well. So that would lead to less dissipation and keep their resonant chains tighter. The calculation of those effects, the cooling and the blanketing and the magma, all of that is yet to be done. So these are new results to try to explain theoretically. Now, I've been hinting at oceans on these planets in TRAPPIST-1. Well, rocky planets that have Earth-like oceans should have could have more dissipation than just the rocks could give. Because remember, I said that Earth has a value of 20, or I think 40 was on the slide for Q. So if a copy of the Earth were transported to TRAPPIST-1 and dissipated there, it would spread. It would cause the ocean tides would cause the chain of planets to spread even more than we observe. Unfortunately, for the Earth, the continents have been moving around. Dissipation has changed over the time. So there's like so many more complications in an ocean-bearing planet than we've been able to model here. But what's exciting is that we have a way to, around a very distant star, start to address what the interiors of the planets are like. So that is all for the presentation. I would love to spend some time taking questions. Okay, thank you. I will start with the gentleman in the back.
Do the patterns of resonant chains seem to be similar regardless of spectral class of the star they orbit?
It's a great question. I can't really make that. I can't see or expect to see a difference yet, just because only TRAPPIST-1 it has a very small star. Most of the other ones are very close to the sun. HR 8799 is a bit more massive, like I think 2 solar radius. It has gas giants, and GJ876. Now I'm thinking about all 10 of them. So GJ876 is also a smaller star, like 0.3 solar radii, and it has gas giants as well. So what I have noticed is that the gas giants tend to like 2-to-1 resonances with each other, whereas the smaller planets tend to like 3-to-2 and 4-to-3. That could be due to migration reasons, that the faster migrating small planets can jam their way past 2-to-1 on the way to 3-to-2 or 4-to-3. That's the going hypothesis. All right, more questions? Yeah, gentlemen, yeah.
Forgive a rookie question here, but the mechanics of making these observations, if the exoplanet's plane of orbit, if we were looking at an equatorial view, we would see a maximum transit.
Yes.
It would be like a straight line.
Right.
But if you pictured that starting tipping toward a polar view, by the time it got to a polar view, we would see a smaller and smaller arc as it approached the polar view, and then it would disappear completely.
Well,
How do
you don't have to get very close to a polar view for the transits to disappear. In fact, the stars are very, very small compared to the orbits of the planets, so you only need to tilt it by a few degrees until you'll miss the transits entirely. So,
How do you correct for the orbital plane of the exoplanets?
well, that's part of the orbital. That's part of the fit to the data. What is so we can derive what the inclinations are. In our conventions, 90 means edge on,
Yeah.
equatorial, and so typical inclinations are 88 degrees, something like that. And if you get to, for orbital periods of tens of days, if you get to 87 degrees, it stops transiting. So what I'm saying is we do notice that we're sensitive to very planar systems, indeed. This has been a preoccupation of mine in my research, is exactly how planar the systems are. And it turns out that of all these systems I showed on that video, for instance, the typical value is a little bit closer to a plane than even in the solar system. You know, the solar system is famously coplanar to just a few degrees. And from that, Laplace and others, well, Kant, they said that we came from a gaseous disk that had dissipation and flattened out like a spinning pizza dough. But that same property is in evidence for all these other systems. Of course, we're biased against the other case of very misaligned systems. Those can be seen in other ways of detecting planets. Okay. Yes.
So, since you're only detecting the planets that happen to be aligned
Right.
for equatorial transit, what's the implication for, what's the percentage that you're able to determine, and then what's the implication for the extrapolation for the number that you're not seeing?
Right. So, of course, it's always the case that even if the system is perfectly coplanar, we're not necessarily in that plane. So we might be seeing the inner planets of a much broader system. The outer planets just stop transiting as they get to larger orbits. And so, yeah, we do think that we do frame the statistics as we're best at probing the inner parts of the system. Now, there can be mutual inclinations of a few degrees even among the inner parts of the system, and then you could miss a planet. That's been a preoccupation of mine also, like predicting whether there's a missing planet between two planets. So you'll notice, let's go back to one of these first plots here. Okay. What's plotted here are non-adjacent planets. So if you have 3 planets and you plot the ratio between the planets 1 and 3, that gives you periods of just 3 days to 10, period ratios of 3 to 10, say. So if you have a period ratio of 4, you could stick a planet in the middle and incline it enough so it doesn't transit. You could have a 4 to 2 to 1 chain and you're missing the middle one. So yeah, we can play those games and try to come up with how many we think we're missing. And with a student, I'm not sure he was listed on the title slide, it was Greg Gilbert. We did a machine learning-esque statistical model of all of these systems and found that we think we were missing about 8 planets, for which there was a very nice gap that looked like it was really calling for a planet, and so yeah, we're sure that we're missing some planets that way.
Oh, but what I meant was that obviously most systems are not going to be inclined equatorially.
Right.
So
Okay.
So what I'm saying is you're getting a very, very tiny number of. So
Yeah, that's why 180,000 systems needed to be surveyed in order to detect about 4,000. So the ratio of detected, because it's fortuitously aligned with us, versus undetected is about 50. So yeah. Yes.
Okay, so you didn't indicate, I don't think, unless I missed it, how far away these stars are. So we're looking back in time because they're like taking that time to get to us.
They're all in the Milky Way though, so it's not a large fraction of their age or anything.
But so based on your analysis, could you determine well, eventually maybe this planet will get kicked out and stop transiting? Can you do that kind of predictions with this modeling and eventually see or predict when that transiting would stop?
Great question. Wow, you're just like ticking through my whole research agenda here. So, the question is how far away they are. The answer is several hundred parsecs to 1,000 parsecs, meaning up to a couple thousand, maybe 5,000 light years is the furthest in this data set. And so that means that, it's a small fraction of its age. We wouldn't have expected that it would have done anything really dramatic in the time that it took that light to pass. But we do expect that being really close in and torquing, having some of them have rather high masses, they should torque each other. If they're out of the plane from each other, they should precess, so they're kind of hula hooping around. And that time scale is a couple hundred years. So with the 4-year survey, all we hoped to see and all we did see was the orbital plane changing slowly, going up the star or going down the star. That was detected in 15 systems out of the 4,000. Just a couple of them were really high signal to noise and the others were like barely detected. So basically I'm saying we can detect the planets perturbing each other in the plane. Like I showed, that's the transit timing variations, because you can so well detect the time of transit. But this effect that we're talking about now, it's much longer time scale, so then you only see a part of it and it's harder to detect.
Even with those rapid systems, like three-day orbits?
Yeah.
Okay.
Yeah, so the transit timing variations we found about, my collaborators found about 260 out of the 4,000 had timing variations, and 15 of them had orbital plane torques out of the plane. Yes?
So in the beginning of your talk, you stated that you think about half the stars have planets.
Right. So that's the correction for the
Right.
non-transiting
That's kind of a
ones.
follow-up on that line of sight, two gentlemen.
Exactly, yeah.
How do you predict that when you don't know the distribution of those orbital angles?
Okay,
I mean,
well,
if you only
packaged in that
5,000
statement.
out of 180.
Packaged in that statement is the assumption that we're not a special observer, and these planetary systems are isotropically oriented with respect to the galaxy. So that's defensible, I think, because planetary systems come from a very turbulent cloud. That's their origin stories that almost every newborn star has a disk. By angular momentum reasons, it's hard to get all that material down to the center, and it falls into a disk and flattens out. But that original angular momentum that went into each star system is coming from a very turbulent cloud where everything's going every which way. So if indeed planetary systems are oriented every which way within the galaxy, and we're just looking at them from some perspective, there's no correlations. So all that is to say, we can only see 1/50th of the orbits from a completely isotropic distribution.
So if Kepler looked in the same plane, let's say the Milky Way,
Yeah.
because that's a disk, and then it looked 90 degrees above that in a survey, you're saying it would be the same distribution.
I'm asserting it would be, yeah.
But I think that'd be an interesting experiment, right?
You mean, okay, so Kepler did look near the plane of the Milky Way, just maybe 10 degrees off, something like that.
But then did it look-
So it could, in principle, look perpendicular.
Right.
But really, that's the experiment Tess is doing. So we already have it in hand. I guess we could test that. Yeah. So Tess is looking all over the sky. And so you could make bins of angle with respect to the galaxy and do that test. Interesting idea. Okay, can we go to a second round of questions? Yes.
Oh, how many of these stars would have light dips that are significant enough so that they'd be detectable with, say, a amateur astronomer-sized telescope
Oh,
and
great question.
And a CCD?
Yeah, so what's fantastic about the transit method is it's the most accessible to amateur methods. Unless, microlensing, if you get a big team together, you can do microlensing also. But yeah, so not the ones from Kepler, but the ones from TESS, definitely. There's a lot of 1% deep dips. That's possible to do. I've done it with a telescope we have access to, that's a 50 centimeter mirror, so that's pretty big. But you can do it with 10-inch diameter telescopes pretty easily. I mean, the TESS cameras are not very big. I think it's something like 10 inches. So yeah, it's quite possible. The difficulty is getting comparison stars and getting photometric nights that aren't plagued with clouds, and but yeah, it's quite possible. Yeah.
Yeah, there's a piece of reasoning I failed to follow, I think.
Okay.
Because you showed a couple systems and talked about Q, about the sort of quality and factor of the dissipation, and
Yeah.
that you could learn something, you said, if you assume that number was the same for all the planets in a system.
Right.
And I think when you got to TRAPPIST-1, it seemed to me that you started having different Qs. And I'm wondering, like, is that a good assumption that they're all the same in the same system? Or like,
Right. So
maybe you can learn something that way, but you can learn more if you relax that assumption? So,
okay.
did I go off the rails somewhere? Yeah.
Made that assumption here,
Uh-huh.
and the reason I did it is because more than one planet could in principle contribute to the dissipation. And so I would expect the innermost planet to have the biggest it should have the largest tidal forcing, but that doesn't mean its dissipation will be it won't necessarily contribute the most to the energy dissipation which causes the system to spread. So if it has a high Q and the next planet out has a very low Q, then it could be dominated by that next planet. So I'm just trying to be rigorous in what my stating all my assumptions. In practice, the planets of, let's get the plot up here. The planets of Kepler-60 have moderate, like very small differences. This is a 5-4 resonance and a 4-3 resonance. So these planets are not that much further from the star than the inner planet. So they're going to have similar sized tides. So the system for which this assumption is most important is Kepler-60. Whereas Kepler-80, they're spread out more, so it's probably due to most of the dissipation will be on that one. TRAPPIST-1, I explained that the inner two should be very circular, so then it should be the next one that matters. But this isn't it. I mean, this is definitely a limitation to this method. that you can't be absolutely sure which of the planets is dominating the dissipation. Okay, and then over here.
More of a basic question. One of the first charts showed Kepler 30, E, C, and D, I think. Are those the light curves you were showing?
Yeah.
So if, like, 30C has a bigger dip, but not quite as wide versus D, what does that tell you, if anything, about the size of that orbit?
The dip tells you the ratio of areas of the planet and the star. So the easiest one to do is a 1% deep dip. The square root of that is 10%. So the ratio of areas, square root of that would be the ratio of radii. So in this system, you have a planet that's a little bit bigger than Jupiter, transiting a sun-like star. That would be C. And then the inner planet is much smaller, and as you can see, so it's more like Neptune in size. Now the duration, how long it stays on the star, that mainly has to do with its orbital speed. Okay. Also, of course, the exact inclination, as we were discussing earlier, because if the planet has an inclination of, let's say, 87 degrees, it could just barely clip the edge of the star. So let's assume that they're all marching across the middle of the star. Well, then the time they spend on the star will be inversely related to their velocity. Their velocity you can just pick up from Kepler's law, or the exoplanet version of that, which Newton can give you if you know the mass of the star. So assuming that they're all pretty much on near circular orbits, then you can calculate the velocity across the star and make the correction for that factor. So yeah, basically I'm saying it's natural for the outer planets with longer orbital periods to be orbiting slower, and that gives you a longer duration. Yeah.
And then I just have a question. Have these studies helped us understand the migration of our own solar system over time better?
Yeah. What's the connection to our own solar system? Well, the Kepler 223 system is perhaps like a fossil or an example of what our own giant planets might have done in the past. Around 2008, there were a few studies published of the giant planets of the solar system saying after they formed in the gaseous disk that they might have migrated into resonance with each other, and only the action of planetesimals, or what the remnants of which are the Kuiper belt objects, gravitationally interacting with this set of 4 planets is what spread them out to where they are today. So just, yeah, as a background, our gas giants and ice giants, Jupiter, Saturn, Uranus, and Neptune, they are not in a resonance, but Jupiter and Saturn are near 5 to 2, and then Uranus and Neptune are near 2 to 1, I think it is, but not as near as the systems I've been talking about. And so if they had a history of being in a resonant chain like the systems we were talking about, they had to have spread pretty far away from it since then. So like I'm saying, they're not close enough into the star for tides to do that, but acting by a bunch of planetesimals, and I mean a lot, like 30 or more Earth masses of planetesimals scattering off them could cause them to spread back out. So that's a going theory in the field. That's actually, so Nature magazine tends to like get into grooves on publishing topics that it thinks is sexy. So it published a bunch of those articles about the solar system's history, and that's one reason why we were able to get into the Nature for that article on Kepler 223 is because we said this could be an example of an early stage of the solar system. Okay, here.
So when one of your slides said Planet D dominated the environment,
The dissipation.
you're talking about the dissipation. Okay.
Yeah.
Just so it's what? So does Jupiter do that for our solar system? And just because of its mass, or?
Yeah, so the mechanism I just talked about with planetesimals scattering around,
Yeah.
they tend to make Uranus and Neptune move out further, just because it's a reaction to scattering that Uranus and Neptune are moving out. And then when those planetesimals come near Jupiter, it's so massive that it can eject them without moving much itself. So the spreading is mostly in the smaller planets in the case of the solar system. But it is important for Jupiter to be massive enough to cause that ejection. So one could say that, Jupiter's mass dominates the effect as a whole. What I meant about dominating in these resonant chains was what we were talking about over here, is can we attribute all the energy that went to spread the chain just to one planet? Yes?
Are these transits best observed at optical frequencies, or are there other parts of the spectrum where they would be more easily seen and perhaps down the road be detected with, say, space-based gravitational wave equipment or something?
Great question. So it's mostly best to detect these in the optical, yes, especially for all the planets around sun-like stars. TRAPPIST-1 is a special case because it's such a low-mass star that most of its radiation is coming out in the infrared. So a near-infrared, it was the Spitzer Space Telescope, I think at 3 microns, that detected the best transits for this one. And then, can gravitational waves ever be used for this? There has been that suggestion. So in the future, we will have a space-based gravitational wave detector called LISA, and it should be able to detect binary orbits, like two white dwarfs around each other. If they have a short orbital period, like less than 10 minutes, I think, then LISA will be able to pick it up. And then it's going to fly for, a decade or two, and then be able to see exactly what the phasing of that orbit is. And I have seen a published paper saying an exoplanet could be discovered around such a binary because it will shift the center of mass of the binary as the 3 orbit around each other, and so then the phase of the signal will be earlier or later based on the finite speed of light traveling across the system. So, kind of a Rube Goldberg answer, but yes, gravitational waves might be able to detect an exoplanet someday. Not in transit though. That's a different concept. All right. Any other business? I think you have a business meeting to do, right? All right. Well, thank you for having me.